A wall of logs, 50 feet high, holding back a reservoir containing 50 million gallons of water, and you're about to blow it up. The dam is built from the same logs you're trying to transport downstream. 10,000 logs stacked and interlocked to create a temporary barrier across a river. Behind the dam, water has been accumulating for weeks, flooding the valley upstream. Logs are floating on this artificial lake. 20,000 logs waiting to be transported. When you blow the dam, 50 million gallons will surge downstream in minutes, creating an artificial flood powerful enough to carry logs 20 miles in an hour. The wavefront will be 15 feet high, traveling faster than a horse can run. Everything in its path will be destroyed. Bridges, buildings, anything not designed to withstand a flash flood. But that's acceptable because this river doesn't naturally have enough water to float logs. So you create the water by building a dam, waiting for it to fill, and then releasing it all at once. This was splash dam logging. Building dams from logs to flood rivers with logs. And it worked for half a century before anyone realized it was devastating the rivers themselves. This was logging in the Pacific Northwest, the Northern Rockies, and parts of the Midwest from the 1880s through the 1930s. Timber operations were cutting forests in steep mountain terrain, where rivers were the only practical transportation route.
But these mountain streams had a problem. They didn't carry enough water year-round to float logs reliably. In spring during snowmelt, they might have adequate flow, but by summer and fall, the water level would drop and logs would strand on gravel bars. The solution was to create artificial spring runoff whenever you needed it. Build a dam, fill the reservoir, release the water and logs together in a controlled flood that would sweep everything downstream to mills or larger rivers where log booms could collect them. Could you really build a dam 50 feet high using only logs and manual labor? Could you accumulate enough water to create a flood wave that would carry 20,000 logs 20 miles downstream? And could you do this safely when releasing that much water that fast was essentially creating a weaponized flood? The answer is yes. The evidence exists in photographs showing massive log dams and their releases, in engineering records documenting splash dam construction, and in the river channels that still show the scars from decades of artificial floods. Before we get to how splash dams worked, you need to understand why they were necessary. Because this wasn't just about convenience. In many logging regions, splash dams were the only economically viable way to transport logs from forest to mill. The geography of Pacific Northwest and mountain logging created specific transportation challenges. The timber was in steep mountain valleys.
The mills were downstream, often 50 to 100 miles away. Between forest and mill, the terrain was too steep and rough for wagon roads or railroads in many areas. The rivers provided natural corridors through the mountains, but they weren't navigable by conventional means. They were too shallow, too full of rapids and boulders, too variable in flow. During high water, they'd be raging torrents. During low water, they'd be series of pools connected by shallow riffles. The spring log drives used on rivers with adequate natural flow wouldn't work on these streams. A conventional log drive waited for spring snowmelt to raise water levels, then floated logs downstream with the natural current.
Men called river drivers would work from riverbanks and in boats, keeping logs moving and breaking up jams. But this required sustained high water for weeks, enough time to move millions of board feet of logs downstream. Many mountain streams simply didn't have sustained high water. They'd have a brief spring peak, then drop to low summer flows within weeks. The splash dam solved this problem by storing water and releasing it on demand. Instead of depending on natural hydrology, you'd create your own hydrology. The concept was simple. Build a dam across the stream at a suitable location. The dam would pond water upstream, creating a reservoir. Logs would be placed in this reservoir. When you had enough logs and enough water, you'd open the dam suddenly. The reservoir would drain, creating an artificial flood wave. The logs would be carried along with the flood, traveling downstream at high speed until they reached their destination or the flood wave dissipated. The construction of splash dams required finding the right location. The ideal site was a narrow section of valley where a relatively short dam could impound a large volume of water. Rocky canyon walls were better than soil banks. The rock would contain the reservoir more reliably. The site also needed to be accessible for construction and positioned where the released flood would travel the desired distance downstream without hitting major obstacles that would cause jamming. The dam construction used logs as the primary structural material. This might seem counterintuitive, using logs to build a dam to transport logs, but it made economic sense. The logs for the dam were lower quality timber that wouldn't make good lumber. Crooked logs, knotty logs, logs from smaller trees, anything unsuitable for sawing could be used in dam construction. Some dams were built primarily from logs cut specifically for the dam, but many used logs that wouldn't otherwise have commercial value. The selection of logs for dam construction required judgment. The logs had to be large enough to provide structural strength, typically at least 12 inches in diameter. They had to be reasonably sound, not rotted or severely damaged by insects. And they had to be available in sufficient quantity near the dam site to avoid expensive hauling. A major splash dam might require 5,000 to 10,000 logs. Hauling that many logs long distances would be prohibitively expensive, so dam sites were chosen partly based on proximity to suitable timber. The basic structure was a crib dam, horizontal logs laid in layers, each layer perpendicular to the layer below, creating a massive lattice structure. The crib would be filled with rock, dirt, and brush to make it watertight. The downstream face might be sheathed with planks for additional water tightness. The upstream face would be sloped to resist water pressure. The base would be wider than the top, creating a triangular profile when viewed from the side. The engineering calculations for splash dams were crude by modern standards, but based on sound principles. The structure had to resist the horizontal force from water pressure, which increases with depth. At 50 feet of depth, water pressure is about 22 pounds per square inch. Over a 200-foot-long dam face, that's tremendous total force, millions of pounds. The dam had to be massive enough that its weight and friction would resist this force without sliding or overturning. The construction sequence started with site preparation. The riverbed would be cleared of loose material down to bedrock or solid substrate. If bedrock couldn't be reached, pilings, sharpened logs driven vertically into the ground, might be used to create a stable foundation. The foundation work was critical because any settling or shifting after the dam was complete could lead to failure.
The first course of logs would be laid directly on the foundation, positioned perpendicular to the river flow. These logs might be 16 to 20 inches in diameter, the largest available, because they'd bear the weight of the entire structure above. The logs would be notched where they cross to create interlocking joints. Wooden pegs or iron spikes would secure the joints. Some builders used iron rods, driven through multiple log layers to pin the structure together. The second course would be laid perpendicular to the first, creating a crosshatch pattern. The gaps between logs would be filled with smaller logs, branches, and brush.
This fill material served multiple purposes. It added weight to the structure, it reduced the spaces through which water could leak, and it created friction that helped lock the logs together. As layers were added, the structure would grow both upward and outward, creating the sloped upstream and downstream faces. The rock fill was added as construction proceeded. Workers would gather rock from nearby sources, the riverbed itself, or talus slopes, or quarried stone if available. The rock would be carried or hauled to the dam and placed in the crib spaces between logs. The rock added enormous weight. Stone is 2.5 times denser than water, so a cubic yard of rock-filled crib weighed over 2 tons. This weight helped anchor the structure and resist water pressure. The upstream face was typically sloped at about 45 degrees from vertical. This slope served two purposes. First, it distributed water pressure over a longer surface, reducing the tendency of water to lift or penetrate the structure. Second, it increased the weight of the dam by making it thicker at the base. The downstream face was steeper, often nearly vertical, to minimize materials while still providing stability. The crest of the dam, the top surface, was the control point for the maximum reservoir level. The crest would be built to a specific elevation that determined how high the water could rise. Building the crest level was important because an uneven crest would create uneven water pressure and potential weak points.
Builders use simple leveling instruments, water levels, or builder's levels to ensure the crest was horizontal. A typical splash dam might be 50 feet high and 200 feet long at the crest. The base would be 100 feet thick, tapering to 20 feet at the top. The volume of logs in such a dam could be several thousand. 10,000 logs was a reasonable estimate for a major dam. The construction time ranged from several months for a large dam to a few weeks for a small one. The work was done by logging crews during periods when logging wasn't practical, typically late summer and fall when the ground was dry. The labor requirements for dam construction were substantial. A crew of 30 men might work for 3 months to build a major dam. The work was physically demanding, cutting and hauling logs, lifting and positioning heavy timbers, moving rockfill. The workers used simple tools, axes, saws, pry bars, rope, and horse or ox teams. There was no powered equipment. Everything was done by muscle power, human and animal. The safety record for splash dam construction was poor. Working on partially completed structures that might be 40 feet high, handling heavy timbers, working near rivers, all of these created hazards. Falls were common. Being struck by logs being positioned was a constant danger. Some workers drowned when they fell into partially filled reservoirs. The injury and fatality rate for splash dam construction was probably comparable to logging itself, high by any standard.
The testing of completed dams was done by gradually filling the reservoir and watching for problems. The first filling was the most critical. As water pressure built, weak points in the structure might reveal themselves: leaks, settling, movement. Some dams failed during first filling, requiring repairs or rebuilding. The builders would monitor the dam constantly during initial filling, ready to open release mechanisms if dangerous problems developed. The maintenance of splash dams between uses required periodic inspection and repair. Leaks had to be plugged. Logs that had deteriorated had to be replaced. The fill material might settle, requiring additional rock or brush. Some dams lasted decades with regular maintenance. Others failed after a few uses, requiring complete reconstruction. The release mechanism was the critical component. The dam had to be able to hold 50 million gallons or more, then release it all rapidly when triggered. Different designs used different release mechanisms. Some used removable sections, timbers that could be pulled out to open a gap. Others used explosive charges, dynamite placed in the dam structure that could be detonated to breach the dam. The most sophisticated used gate structures, wooden or steel gates that could be opened to release water in a controlled manner. The removable section design used specific timbers, called trigger logs or key logs, that could be pulled out to initiate failure. These timbers would be positioned in the dam structure such that removing them would cause a section of the dam to collapse.
The trigger logs might be held in place by chains or cables that could be released from shore. Workers would attach ropes or cables to the trigger logs, position themselves safely on shore, then pull the logs free. Once the trigger logs were removed, water pressure would push through the gap and quickly enlarge it, leading to full dam failure. The explosive release method used dynamite charges placed in the dam structure during construction. The charges would be positioned at critical points, typically near the base of the dam where water pressure was highest. Blasting caps and fuses would be attached, with the fuses running to shore where they could be lit safely. When a release was planned, workers would light the fuses and retreat to high ground. The explosion would blow a hole in the dam, allowing water to surge through. The water erosion would quickly expand the breach, leading to complete failure within minutes. The amount of dynamite needed depended on the dam size and construction. A small dam might require 10 to 20 sticks of dynamite.
A large dam could require 50 to 100 sticks. The explosives were expensive. Dynamite cost about 20 cents per stick in 1910, equivalent to $6 in modern currency. For a large blast using 100 sticks, that's $600 in modern money. But this was acceptable compared to the cost of alternative release methods, or to the value of the logs being transported. The gate mechanism design was the most sophisticated, but also most expensive. A gate would be built into the dam structure, essentially a large door that could be opened to release water. The gate might be wooden planks in a frame, or in later designs, steel plates. The gate would be held closed by the water pressure during filling. To open it, a mechanical advantage system would be used. Levers, winches, or counterweights that could overcome the water pressure and pull the gate open. Gate mechanisms allowed for more controlled releases. Instead of catastrophic dam failure, the operator could open the gate gradually, controlling the release rate. This created smaller flood waves that were less destructive downstream, but still effective at moving logs. The disadvantage was cost and complexity. Building a gate mechanism might double or triple the construction cost of the dam. Most logging operations used simpler explosive or trigger log methods, despite their less controlled releases. The timing of releases was critical to effectiveness. The reservoir had to be full or nearly full to generate adequate flood volume. But filling took time, weeks or months depending on stream flow and reservoir size. The logging operation had to coordinate log delivery with reservoir filling, so logs would be ready when the water was. And the release had to be timed for conditions downstream, releasing when mills were ready to receive logs, when weather was favorable, when crews were positioned to handle jams. The flood wave from a splash dam release was tremendous. 50 million gallons, roughly 75 acre-feet of water, draining in 10 to 15 minutes, creates an average flow rate of 50,000 gallons per second. But the release wasn't uniform. The initial wave was the largest, perhaps containing half the reservoir volume. This wave might be 10 to 20 feet high, traveling at 10 to 20 miles per hour. Behind the initial wave, the flow would gradually diminish as the reservoir emptied. The physics of the flood wave were complex. As the wave traveled downstream, it would interact with the river channel. In narrow sections, the wave would be higher and faster. In wide sections, it would spread out and slow down. Bends in the river would deflect the wave, potentially causing it to overtop banks and flood adjacent areas. Rapids and waterfalls would aerate the water, increasing its destructive power. The wave would carry tremendous kinetic energy, the energy of millions of gallons moving at high speed. The erosive power of splash dam floods was extraordinary. The high-velocity water would scour the riverbed, removing gravel, sand, and even boulders. The turbulence would undercut banks, causing them to collapse into the flow. Trees growing along the riverbank would be uprooted and carried downstream. The channel geometry would be permanently altered. Pools would be filled with sediment. Riffles would be scoured deeper. Meanders would be straightened or enhanced depending on flow patterns. The sediment transport during splash dam releases was measured in tons per minute. Normal stream flow might carry a few pounds of sediment per minute. A splash dam flood might carry tons. The sediment would be deposited downstream when the flood wave dissipated, creating bars and filling pools. Over decades of repeated splashes, some streams accumulated meters of sediment in their lower reaches, while having their upper reaches scoured to bedrock. The logs in the reservoir would be caught by the wave and carried downstream. 20,000 logs floating in a reservoir would become a chaotic mass when the wave hit. Some logs would be tumbled end over end. Others would ride the wave like surfboards. The logs would jam together, separate, collide with rocks and riverbanks. The sound would be tremendous. The roar of rushing water combined with the crashing and grinding of thousands of logs in motion. The behavior of logs in the flood was unpredictable. Lighter logs, from trees with low-density wood like cedar or pine, would float higher and travel farther. Heavier logs, from dense hardwoods or waterlogged softwoods, would travel deeper in the flow and might strand sooner. Long logs would tend to orient parallel to the flow. Short logs would tumble chaotically. The ideal log for splash dam transport was medium length, moderate density, and freshly cut so it hadn't absorbed much water. The jamming of logs was the primary operational problem with splash dam logging. Logs would collect at obstructions, against bridge pilings, at river bends, where the channel narrowed. A jam might contain hundreds or thousands of logs piled in a chaotic mass. The jam would block the river, causing water to back up behind it. Breaking a jam required workers, called jam breakers, to work in extremely dangerous conditions, using PVs and dynamite to break apart the log pile and get it moving again. The distance traveled by the logs depended on the size of the release and the river gradient. On steep streams, logs might travel 20 to 30 miles before the flood wave dissipated and logs began stranding. On gentler streams, the distance might be only 5 to 10 miles. The logging companies would plan for this, building multiple splash dams at intervals along a river so logs could be moved in stages from the logging area to the mill or to a larger river. The recovery of logs after a splash required crews working along the entire river reach where logs had traveled. Workers would walk the riverbanks looking for stranded logs. Logs stuck on gravel bars would be rolled or pried back into the water. Logs in side channels would be redirected to the main flow. The work continued for days or weeks after a splash, until all commercially valuable logs had been recovered or accounted for. Some logs would be lost, stuck in inaccessible locations, buried in sediment, or swept so far downstream they couldn't be found. Among the workers who operated splash dams was a man named Eric Johansson, a Swedish immigrant who worked on splash dam operations in Washington state from 1895 to 1915. Johansson's diary, preserved by his family, describes the construction and operation of splash dams. From August 1902, describing dam construction. We are building a splash dam on the North Fork. The dam will be 50 feet high when complete. We have been working for 2 months. The crew is 30 men. We fell trees for the dam structure and haul them to the site with horse teams. The logs are placed in layers, each layer perpendicular to the last. We fill the spaces between logs with rock and brush. The work is hard, lifting and positioning heavy logs all day. But the construction is fascinating. We are building a structure that will hold back a small lake, and it is made entirely from logs. Johansson describes a later release. Today we released the dam. We had been filling it for 3 weeks. The reservoir behind the dam was perhaps 40 acres and contained maybe 30 million gallons. We had 20,000 logs floating in the reservoir, ready to ride the splash downstream. At noon, we detonated the charges. The explosion was loud, but the sound of water was louder. The dam blew apart, and water surged through. The wave front was 15 feet high. The logs were caught up and swept downstream in a chaotic mass. We watched from high ground as the wave traveled down the canyon. Within an hour, the reservoir was empty.
What had been a lake was now a muddy depression with scattered debris. Another documented worker was Patrick Murphy, an Irish immigrant who worked as a splash dam superintendent in Oregon from 1905 to 1920. Murphy's letters to the lumber company, preserved in company archives, described the logistics and challenges of splash dam operations. From May 1910, the North Fork Dam is complete and has filled satisfactorily. The reservoir contains approximately 55 million gallons. We have 16,000 logs in the reservoir ready for release. The weather forecast is for clear conditions for the next 3 days, which is ideal for a splash. I propose to release on Wednesday at 2 o'clock in the afternoon.
This timing will allow the splash to reach the mill pond by early evening while there is still daylight for sorting logs. I have positioned crews along the river to watch for jams and to rescue any logs that strand. The dynamite charges are in place and ready. Murphy's letters also describe problems. The splash released yesterday did not perform as expected. The initial wave was adequate, but dissipated quickly. Many logs stranded within 10 miles of the dam. I believe the reservoir was not full enough. We should have waited another week for more water. Now we have perhaps 5,000 logs scattered along 15 miles of river. We will have to build smaller splashes at intervals downstream to move these stranded logs. This will cost time and money.
The mill superintendent is very displeased. A third documented worker was Takeshi Yamamoto, a Japanese immigrant who worked on splash dam construction crews in Idaho from 1908 to 1918. Yamamoto's account was recorded in an oral history project in 1950. He described both the construction work and the dangerous nature of splash dam releases. According to the interview, I worked building splash dams for 10 years. The work was hard. We cut logs, hauled them, built the dams. The construction took many weeks, sometimes months for a big dam. We would build the dam in late summer when the river was low. By spring, the snow melt would fill it. Then we would release. The release was the dangerous part. We used dynamite to blow the dam. Everyone had to get to high ground before the blast.
I saw men get caught by the water. If you were in the river channel when the splash came, you died. The water was too fast, too powerful. I saw 3 men die over the years I worked. One was hit by a log and killed instantly. 2 were caught by the flood and drowned. Yamamoto described the spectacle of releases. The splash was something to see. The wall of water would come down the canyon carrying thousands of logs. The sound was like thunder. The ground would shake. Trees along the riverbank would be torn out. Boulders would be moved. After the splash, the river looked like it had been through a war. Everything was changed. The channel was wider, deeper, different. We changed the rivers with our splashes. The environmental impact of splash dams was severe and long-lasting. The artificial floods scoured river channels, removing gravel beds where fish spawned. The logs tumbling downstream would batter the riverbanks, destroying streamside vegetation. The floods would flush out pools and undercut banks, changing river morphology. The accumulation of woody debris from decades of splash dam operations would alter stream flow patterns. The salmon runs were particularly affected. Pacific salmon spawn in gravel beds in mountain streams. The female salmon digs a nest, called a redd, in the gravel, deposits eggs, and covers them. The eggs need clean gravel with water flowing through it to survive. Splash dam floods would scour out these gravel beds, destroying eggs and disrupting spawning habitat. The floods would also alter the gravel distribution, removing gravel from some areas and depositing it in others, making the stream less suitable for spawning. The riparian vegetation along streams, the trees, shrubs, and plants growing on the banks, was destroyed by repeated splash dam floods. This vegetation stabilized banks, provided shade that kept water cool, and contributed organic matter to the stream ecosystem. When splash dams removed this vegetation, the streams became wider, shallower, warmer, and less productive for fish. The scale of splash dam operations in some regions was extraordinary. In the Clearwater River drainage in Idaho, over 50 splash dams were built between 1900 and 1930. These dams moved an estimated 2 billion board feet of logs, roughly 400 million logs, over 3 decades. Each splash dam might be released 10 to 20 times per season, creating hundreds of artificial floods per year across the drainage. The Clearwater operations were documented in detail by the U.S. Forest Service because much of the timber came from national forest lands. The records show the systematic development of splash dam infrastructure. The first dam was built in 1900. By 1910, there were 15 dams operating. By 1920, over 40 dams were in use. The system had been expanded to cover virtually every tributary stream with adequate gradient. Logs cut anywhere in the drainage could be moved through the splash dam system to reach the Clearwater River main stem, then floated to mills in Lewiston. The coordination required for such a system was substantial. A central dispatcher would coordinate releases across multiple dams to ensure logs moved efficiently through the system. If Dam A released, but Dam B downstream wasn't ready to release, logs would pile up between the dams. If Dam B released before Dam A, the downstream splash would be wasted. The optimal sequence was to release dams from upstream to downstream in timed succession, so logs from the upper splash would arrive at the next dam just as it was releasing, creating a continuous flow of logs and water downstream. The Oregon Coast Range had extensive splash dam operations as well. Companies like the Smith Powers Logging Company operated multiple dams on different streams, coordinating releases to move logs through the system. A log cut in the mountains might ride 4 or 5 splashes over several weeks before reaching the mill, traveling 50 miles in the process. The Smith Powers operation on the Coos River system illustrates the scale of investment in splash dam infrastructure. The company operated 8 major splash dams and numerous smaller ones. The total construction cost for this system was approximately $150,000, $4.5 million in modern currency. But the alternative, building railroads through the mountainous terrain, would have cost over $1 million. The splash dam system paid for itself within 3 years of operation through transportation cost savings. The production statistics from major splash dam operations show their efficiency. The Potlatch Lumber Company in Idaho reported moving 20 million board feet per year through their splash dam system using a crew of about 30 workers dedicated to dam operations. The labor cost was approximately $15,000 per year, about $450,000 in modern currency. Moving the same logs by railroad would have required 100 workers and cost at least $50,000 per year. The splash dam system operated at less than 1/3 the cost of the railroad alternative. The economic advantage of splash dams was significant. Moving logs by railroad or wagon in mountain terrain might cost $5 to $10 per thousand board feet. Moving them by splash dam cost $1 to $2 per thousand board feet, a savings of 80 to 90%. For a company moving 10 million board feet per year, this savings could be $50,000 to $80,000 annually, $1.5 to $2.5 million in modern currency. But the splash dam system had limitations and risks. The primary limitation was geographic. You needed a stream with adequate gradient and suitable dam sites. Flat terrain wouldn't work because the flood wave would dissipate too quickly. The second limitation was seasonal. You needed water to fill the reservoirs, which meant spring snowmelt or fall rains in most regions. Summer operations were often impossible due to low water. The risks were substantial. The main risk was to workers. The releases were inherently dangerous. Multiple workers were killed by splash dam operations over the decades they were used. Some were caught in the flood when releases occurred unexpectedly or when they misjudged the wave timing. Others were killed by logs swept downstream by the flood. Falls while working on dam structures claimed additional victims. The second risk was to infrastructure. A splash dam release would destroy anything in its path that wasn't substantial enough to withstand the flood. Bridges might be washed out. Buildings near the river could be damaged. Small dams for other purposes, irrigation, water supply, might be destroyed. The logging companies sometimes had to pay damages when their splashes destroyed property downstream. The third risk was catastrophic dam failure. If a splash dam failed unexpectedly, from heavy rainfall, earthquake, or structural defect, the uncontrolled release could be devastating. There are documented cases of splash dams failing unexpectedly and sending flood waves downstream that killed people, destroyed buildings, and caused extensive damage. One documented catastrophic failure occurred in Montana in 1908. The Big Creek Splash Dam, holding approximately 80 million gallons, failed during heavy rainfall. The dam had been full but was not scheduled for release. The heavy rain caused the reservoir to overflow, and the overflow eroded the dam structure. The dam failed suddenly, releasing the full reservoir in minutes. The flood wave traveled 15 miles downstream, destroying 2 small settlements and killing an estimated 12 people. An investigation concluded that the dam had been inadequately designed for the reservoir capacity, and that there had been no emergency spillway to handle excess water. Another significant failure occurred in Idaho in 1917. The Lochsa River splash dam failed during construction when workers were still on the structure. A premature settling of the dam under water load caused a section to collapse. The partial failure released approximately 20 million gallons in a sudden surge. 3 workers were on the dam when it failed. 2 managed to escape to high ground. The third, identified in records as Henderson, a rigger, was swept away and killed. His body was found 2 miles downstream 3 days later. The regulation of splash dams was minimal in most jurisdictions during their peak use. The dams were considered temporary structures, not subject to the regulations that applied to permanent dams. There were no requirements for engineering review, no safety inspections, no limits on reservoir capacity or release volumes. The logging companies operated largely without oversight, designing and operating splash dams based on their own judgment and experience. This began to change in the 1920s as the environmental impacts became more apparent and as recreational use of rivers increased. Fisheries agencies began documenting the damage to salmon runs. Sportsmen complained that streams were being destroyed. Some states began requiring permits for splash dam operations and imposing restrictions on when releases could occur. The technology of splash dams evolved over the decades they were used. Early dams were crude structures, loose piles of logs held by gravity and friction. Later dams used more sophisticated engineering, crib structures with rock fill, planked faces, gate mechanisms for controlled release. Some late-era splash dams used concrete in key structural components, though the bulk of the structure was still logs. The replacement of splash dams came primarily from the expansion of logging railroads into mountain terrain. Railroad technology improved in the early 1900s, making it economically feasible to build railroads up steep grades and around tight curves. A railroad could move logs year-round, regardless of water availability. The logging companies gradually shifted from splash dam operations to railroad logging, though the transition took decades. Some splash dams continued operating into the 1940s, in remote areas where railroad construction wasn't economical. The cleanup of splash dam infrastructure was often incomplete or never done. When operations ceased, the dam structures might be left in place. Some would gradually decay and wash out.
Others would remain for decades, creating partial barriers in streams. The cleanup of abandoned splash dams became a restoration priority in many watersheds in the late 20th century, as agencies recognized that the old dam sites were impeding fish passage and disrupting stream ecology. The legacy of splash dam operations is visible in stream channels throughout the former logging regions. Rivers that were subjected to decades of splash dam operations show characteristic morphology: wider, shallower channels, altered gravel distribution, reduced riparian vegetation, embedded substrate. Restoration ecologists can identify former splash dam streams from their physical characteristics even a century after operations ceased.
The cultural memory of splash dams is preserved primarily in photographs and in the accounts of workers like Johansson, Murphy, and Yamamoto. The photographs show the dramatic scale of the operations: massive log structures impounding large reservoirs, release waves carrying thousands of logs downstream. These images document engineering accomplishments that were impressive for their time, but that we now recognize as environmentally destructive. The lessons from splash dam operations are relevant to modern debates about resource extraction and environmental protection. Splash dams worked efficiently for their intended purpose, moving logs economically, but they externalized environmental costs that weren't recognized or valued at the time. The damage to fisheries. the alteration of stream ecosystems, the loss of riparian habitat. These weren't factored into the economic calculations that made splash dams attractive. In modern terms, splash dams were profitable because environmental costs were not priced into the system. This pattern repeats across resource extraction history. Operations that appear economically rational when environmental costs are ignored become recognized as destructive when those costs are acknowledged. The challenge is building economic and regulatory systems that internalize environmental costs, making truly sustainable operations the most economically attractive option. The splash dams that once dotted mountain streams throughout the Pacific Northwest and Northern Rockies are gone now. Some were removed deliberately during stream restoration projects. Most simply decayed and washed away over decades. The reservoirs they impounded have filled with sediment, creating meadows where lakes once existed. The streams have partially recovered their natural morphology, though complete recovery may take centuries. But the evidence of what was done remains. The scars in river channels, the altered fish populations, the changed forest composition in former splash zones, all evidence of a half-century period when artificial floods were a standard logging technique. 10,000 trees built into a dam to flood a river to transport 20,000 more trees. It sounds like madness now, but it was rational engineering given the constraints and values of the time. The workers who built and operated splash dams, people like Eric Johansson building dams log by log, Patrick Murphy planning release timing, Takeshi Yamamoto watching men die in the floods. They were working within the system that existed. They weren't making environmental policy, they were earning wages, using available technology, meeting economic demands. The responsibility for the environmental damage lies not with the workers, but with the economic and regulatory systems that incentivized destructive practices. Today, if you hike along mountain streams in former logging regions, you might encounter evidence of old splash dam operations. An unusually wide section of channel, massive logs embedded in the riverbank, a flat area upstream that was once a reservoir, stone walls that were once part of a dam structure. These remnants are monuments to industrial-scale environmental manipulation. Humans reworking river hydrology to serve economic purposes, using massive temporary structures built from the same logs they were designed to transport. 50 feet of stacked logs holding back 50 million gallons. 20,000 logs waiting to ride the wave. A dynamite blast and a wall of water 15 feet high roaring down the canyon. Logs tumbling in chaos. Rivers permanently altered. Salmon runs destroyed. That was splash dam logging, an engineering solution to a transportation problem that worked brilliantly for its intended purpose while devastating the ecosystems it touched.
It's worth remembering both the ingenuity and the destruction, because understanding both is necessary to avoid repeating the mistakes while building on the lessons learned.